Hello everyone, and welcome to our presentation on real-time embedded systems on core operating system concepts. I will walk you through some of the foundation principles that govern how real-time operating systems manage processes, tasks, and communication. This presentation has been prepared by Ibrahim, Amay, and Vardhan from TEHTC for the submission for the course of RTES for the year 2025. So to begin with, let's understand what a process or a task really is. A process is a dynamic instance of a program in execution. It executes not just the code but also a program counter, stack, data section, and a heap. In embedded and real-time systems, we often use the term task instead of process. Tasks tasks are generally lighter and are designed to behave deterministically, meaning their behavior can be predicted based on inputs. In real-time operating system environments, these tasks are tightly controlled and efficiently managed by the kernel to ensure timing accuracy. Now, understanding the process and the task states. Every process or task moves through a defined set of states. Initially, it's in the new state during creation, then it transitions to ready, where it awaits where it awaits CPU assignment. Once selected, it enters the running state. If it needs to wait for input, output, or an event, it moves to the blocked or waiting state. So it can wait for the IO. Finally, when done, it enters the terminated state. In real-time systems, there are additional states like dormant, which means created but not ready, and suspended, indicating a pause state either voluntarily or by system force. These extra steps help RTOS manage time-sensitive behaviors more effectively. Now moving on to the PCB or the process control block, also known as the task control block. So the operating system keeps track of each process using a structure called the process control block or the PCB. This includes the process ID, current state, CPU register values, memory management info, and much more. Similarly, in real-time operating systems, a task control block or TCB is used. It stores task-specific data like the stack pointer, task ID, priority, and register context. These control blocks are essential for saving and restoring a task's execution state, especially during constant context switching. So now we will go through the entire process life cycle, from process creation to its termination and context switching. In general purpose operating systems like Unix, processes are created using system calls like fork, which duplicates a process called exec, which stands for execution, which replaces it with a new image and clone for creating threads. Termination can be voluntary via the exit function the or forced through signals. In real-time operating systems, APIs like task create are used for task creation and termination. Now, context switching is the process of storing the current task state and loading another's. This is a critical function in multitasking systems and must be very efficient and predictable in real-time operating systems since real-time tasks are deadline driven. Next up, we go through the CPU scheduling algorithms and on optimizing performance. So CPU scheduling determines which task or process should execute next. Several algorithms exist for this. First come, first serve is a simple and non-preemptive but can use long waiting times. SJF or shortest job first minimizes wait time but requires accurate prediction. Priority scheduling executes the most important task first, though it may cause starvation. Round robin assigns each task in a time slice, promoting fairness. These algorithms are critical in balancing throughput, utilization, and responsiveness, especially in systems with multiple concurrent tasks. Now we move to the RTOS basics. Real-time systems are basically designed to meet strict timing requirements. So, like it suggests in the name, real-time operating systems. For instance, an airbag must deploy within milliseconds of an accident. Any delay is a system failure. This is an example of a hard real-time system. On the other hand, something like video streaming allows small delays and is considered soft real-time. RTOS uses scheduling algorithms like rate monotonic scheduling, which prioritizes shorter period tasks, and earliest deadline first, which schedules tasks closest to their deadline. These algorithms ensure timely task completion and system predictability. Next up, we go through the process synchronization to ensure order. In systems with multiple concurrent tasks, synchronization is key to avoiding race conditions. Race conditions meaning multiple threads awaiting on the similar resource. Say process A over here is requiring resource 2, but it is holding resource 1. But process B requires resource 1, but it is holding resource 2, which is required by process A, which is also called as a deadlock. So semaphores are integer variables used to control access to shared resources. Binary semaphores for mutual exclusion, and counting semaphores for resource pools. Now coming to mutexes. Mutexes serve a similar purpose but are more specifically designed for mutual exclusion. Uh, Unlike general semaphores, it allows only one single thread to hold and lock a resource at a single time. Moving on to critical sections, where shared data is accessed. This must be the shared data pool that is accessed must be protected using these tools so that only one process can access it at a time. So one process does not overwrite another process. Good synchronization ensures mutual exclusion, progress, and bounded waiting, keeping the system stable and error free. Now we go to deadlock handling and real time issues. A deadlock happens when tasks are stuck waiting for each other indefinitely. For a deadlock to occur, four conditions must be present: mutual exclusion, hold and wait, no preemption, and circular wait. Handling strategies include prevention, avoidance, like the banker's algorithm, detection, and recovery. In real-time systems, other issues include jitter, variation in execution time, interrupt latency, which means the delay between handling interrupts, and priority inversion, which means when a condition where a low priority task holds a specific resource needed by a high priority one. These can seriously impact system reliability if not handled well. Now we go through the final slide, the inter-process communication. It is essential for coordination and data sharing between processes. Message queues let tasks exchange data asynchronously. Over here, you can see through the diagram, you can asynchronously uh, share the data between the consumers. None of the producers is dependent on the other. They can send it in a single queue and send it out to the other end to the consumers. Coming to the mailbox, mailboxes provide named structured communication channels. So basically, it provides a single source of, say, a drop and go kind of mechanism where a task drops off its posts some data over here, which is taken by another task. Which happens when an interrupt service routine is called. Moving on to pipes. Uh, Pipes are unidirectional and useful for simple parent-child communication. Like it is mentioned over here, parent-child, process-child, simple write and read operations. A child cannot write while the parent is writing, and the parent cannot read while the child is reading. simple and unidirectional, or you can say FIFO type uh, structure it follows. Coming to shared memory is the fastest inter-process communication method, but it requires very careful synchronization. So, like I mentioned previously, uh, in deadlock handling, set of shared resource has to be synchronized perfectly so that no task overrides the other. Moving on to sockets finally. Uh, Sockets enable communication between processes across machines, making them vital for distributed systems. So what it does is it basically creates a two-way communication channel. It establishes it, and something like TCP protocol, where a client and server handshake is necessary. So efficient IPC ensures processes can collaborate without interfering with each other's performance. Uh, Thank you. This is the end of our presentation. We hope it has been informational and it will help you ahead understanding operating system concepts, real-time operating system concepts, and together with real-time embedded system concepts as well. Next up, we have the demonstration of free RTOS, which is a real-time operating system, open source real-time operating system. Uh, we'll be demonstrating it through STM Cube IDE next up after this presentation. Thank you.